Hi everyone, welcome to AWM Pitt Grad Seminar series. So today we have two speakers. First one is Alice Merz. She's a PhD student at Università di Pisa, Italy. And the second speaker is Rachel Elfin. She's a PhD student at Rice University, Texas. So our first speaker, Alice, is going to talk on Markov theorems for knots with symmetries. So please proceed, Alice.
Hi, thank you everyone for the invitation. Thank you to the organizer for the invitation. So as you told, I'm talking about Markov theorem for knots with symmetries, but of course I have to explain a lot of things beforehand. So the plan of the talk will be to start with an introduction about, well, where I will say what I mean by knot, what I mean by link, and what symmetries do I consider. And actually, I will also say something about knot theory and what are the aims of knot theory and what are the normal problems that we deal with in knot theory. In the second part of the talk, I will introduce a group called the break group. This is an algebraic object, but it has a very strong connection with links. And I will make this connection more explicit by explaining what are the Alexander and Markov theorems. And in the end, in the last part, I will tell you more about my research. And so my research was focused mostly on seeing how Alexander and Markov theorem can be adapted to the setting of knots and links with the symmetries that I was talking about beforehand. So let's start with the first part of the talk. So a knot for me is a smooth embedding of S1 into S3. And with S1 and S3, I mean the 1 and 3 sphere. Well, in the image, I consider S3 because we like compact manifolds, but if you're more comfortable with it, you can just think of R3, and it's basically the same, since S3 is just R3 union a point at infinity, compactified at infinity. So this is the definition, but actually most of the times I just will confuse the embedding K with just its image, K of S1. So a knot is a simple closed curve in S3 in general for me. And we normally consider them up to isotopy. A definition of isotopy is just a homotopy that at every time is an embedding. But roughly speaking, it's just that we can move this simple closed curve in R3, like normally without breaking it, without making double points and stuff. And we can just move them around like we would do it in the space, like we move in the space. And this is always the same knot. We are not changing the knot. So let's see some examples. What you see here is a drawing of a knot. So we call this a knot diagram. It's just a projection of the knot on a plane. And we just recall which strands are passing over and which strand is passing under, like in this picture. So here are some examples of knots. This is the easiest knot of all, the trivial knot. Then we have the second most easy knot, is the trefoil knot. It just has 3 crossing. Crossing is just a double point. And it's the easiest that is not trivial. And then we have some more complicated knots, like this one that I drew as an example, the periodic knot and the conway knot. So the second definition we have to deal with is the one of a link. So the formal definition would be that a link is a compact submanifold of dimension 1 of S3 without boundary. So it's just a union of knots, this joint union of knots that can be linked together. So some examples are, well, of course, all knots are links. And these are some examples that are not knots. Here you see the off link has 2 components. And then here I drew some other links just as an example. A fact that is known as not too difficult to show about links is that they all bout an oriented connected compact surface in S3. So inside the 3 space. I recall which ones are the oriented connected compact surfaces because these are all classified. And so these are all diffeomorphic to something like in this picture. So, and they are classified by 2 numbers, basically. So their genus, so the number of holes in the donut, let's say, and the number of boundary components. So here, how many boundary components I have in the surface. And so these two numbers just completely determine the surface I'm considering. And so let's see some examples. If I fix the genus equal to 0 and the number of boundary components equal to 0, we just have a sphere, the easiest of the surfaces. Then if I just increase the number of components by 1, I obtain a disk, another easy example of surface. If I increase the genus and just keep the number of boundary components equal to 0, I obtain a torus, so the surface of a donut. And if I just cut a hole in my torus, I obtain a torus with one boundary component, like in this picture. And I recall that in the previous slide, I just said that a link always bound oriented, compact, and connected surface in S3. And let's see some examples. Of course, for the trivial knot, it's very easy. We just have a disk, and this is recall genus equal to 0 and number of boundary components equal to 1. The Hopf link that I showed before, I drew it in a different way this time, but is these two linked trivial knots. This is as a surface that is just an annulus as a boundary, and the annulus is twisted twice. And this has genus 0 and 2 boundary components. And then the trefoil knot as well, I drew it in a slightly different way this time. And one can see that this surface I tried to draw here, like there are 2 disks and some bands connecting the disks here. This is a torus with 1 boundary component. It's just an argument of Euler characteristic. And so we see some examples of these surfaces, and it's not that difficult to construct a surface that has my knot or link as a boundary. So I did this introduction to tell you something about knot theory and what are the main goals of knot theory. So one goal that is very important is to distinguish, like we want to be able to distinguish knots. So to be able to formally say that, for example, the trivial knot is different from the trefoil knot. How can we do that? We will see later on in the talk. Then another main goal of knot theory is to classify knots. For example, there are 2 websites, the Knot Atlas and Knot Info, that record all the information we have on knots with low number of crossing, like I reported here, the homepage of the Knot Atlas. And a huge part of knot theory is to study topological properties of knots. So, for example, how complicated must be the surfaces in S3 that have my knot or link as a boundary. Here I also wrote D4. With D4, I mean the 4 ball, because knot theory is very connected with 4 manifolds, very connected with 4 manifolds too. And sometimes we study surfaces in a 4 manifold, which is a very interesting field of research. So more precisely, the question in this case would be, what is the minimal genus of a surface? Let's restrict ourselves to S3 for now. So let's see how we deal with these problems in knot theory. Very often, we do everything by studying some invariants. Invariants are nothing more than functions from the set of all links up to isotopy into one set, could be any set, but most of the times you have some algebraic structure. For example, it could be x equal to r or x equal to some polynomial ring. And we see that with invariants, if they're easy to compute, we can distinguish links. That was the first goal of knot theory. In fact, if we can compute this invariant for 2 different links and see that they give a different result, then we can definitely prove that these links are different. And we can also use invariants in a smart way to study some topological properties. For example, we try to find invariants that give bounds on, for example, the genus of the surface we were talking about before, like in this way. If we have that the invariant is always less than or equal to the genus, we can be able to restrict ourselves to a small set of possibilities for the genus, and then maybe be able to point at the correct genus of the knot or link. And why do we do all this? Well, the main goal is to draw a lot of nice pictures, of course, but more seriously, it's interesting per se to study these kinds of things. It's an interesting field per se, but inside topology, it has also very nice connections with the study of 3 and 4 manifolds, and also the study of surfaces inside 4 manifolds, as I was saying a little bit before as well. So this is a small overview about knot theory, and then let's go back to the goal of this talk, and I introduce the symmetries that I like and that I study. So the definition, a strongly invertible knot is a pair, K tau, where K, the first part, is just a knot, and tau is an orientation preserving involution of a string. So involution tau square equals the identity. And we also ask that tau preserves the knot setwise, reversing any possible orientation on K. What I mean of orientation on K is just a choice of a direction on the curve, like if I walk on the curve on a preferred direction, let's say. And if I pick one and tau reverses this one, then it's strongly invertible. Well, I also said here link, although the definition for link is a little bit more subtle, but let's think about knots for this part of the talk. So some examples of strongly invertible knots are drawn here. So we have, of course, the trivial knot is very symmetrical and is preserved by the rotation of 180 degrees around this axis, as you can see. Also, the trefoil knot is strongly invertible, and we can just as well rotate 180 degrees around that axis, and we still obtain the trefoil knot. And here I do some more complicated examples as well. And actually, one can really, these examples are satisfactory because one can always think that tau is a 180-degree rotation around an axis. That's always more or less the case. Of course, this is not the only possible notion of symmetry. We study this particular one because many things, we still don't know many things about strongly invertible knots, so there's still much research to be done. And also for its connection with the study of 4 manifolds and also 3 manifolds with involutions, which is a very interesting field. So let's go to part 2. I told you before that I want to introduce a group. And why do we do that? Because a standard strategy inside topology is to associate a topological object that can be very nice, but quite difficult to treat, to an algebraic object. And so we are trying to do the same here. So braid groups are just groups defined as we see here. Here we have a nice presentation with n-1 generators and some relations. I'm not going into the details of these relations, but let's just say that we can identify the sigma i's with a very topological object. So sigma I can be identified with the set of n strands like this, and just with the I and I+1 make a crossing inside the 2 times 0, 1. So inside this, and the inverse of sigma I is just the same, but the crossing is reversed. So this one is passing over, and this one is the understrand. So what is the group operation here is stacking braids over each other. So like, let's see an example in B3. I drew sigma 1 composed with sigma 1 minus 1, and we see here we have sigma 1, here we have sigma 1 minus 1. We stack them over each other, and since we can move these strands inside the 2 times 0, 1, we can move them and just make them trivial. Let's just slide this one on the left and this other one on the right, make them trivial, and we obtain this, that is the trivial braid. And here I do one of the group relations. So let's see, sigma 1, sigma 2, sigma 1. I just stack them over each other. And here, if we slide this strand on the right, just it has to pass below this strand and over this other one and appear on the right like this. I can do that. And here I obtain another braid that is sigma 2, sigma 1, sigma 2. So actually these are the same because I can just move the strands around and obtain the same thing. So this is a group relation. So how are braids related to links? Well, there is a map that gives from a braid gives you a link. Okay, so here I just drew a schematic of the braid. Here you have to think that we have something here that we don't know, maybe this, I don't know. But if I identify the endpoints of the braid together like this, in the trivial way, like I drew here, I just obtain a link. And a natural question, if you do topology, is like, can we obtain all links like this? And the answer was given by Alexander a long time ago, a century ago, and it's just, yes, we can actually put every link in such a position. And the second next natural question is this one. Since now we know that the function from braids to links, that is the closure function, is surjective. Do we know if it's injective? And this is very easy to solve. No, it cannot be injective because, for example, this very trivial braid, if I close it, I just obtain a trivial knot. And here, if we have the slightly less trivial braid with just one crossing like this, and I identify the endpoints, I obtain this thing. But if I undo this curl, just moving around in the tree space, I just undo the curl, I just obtain the trivial knot once again. So the second most natural question now is, what braids have the same closure then? And this was done by Markov in 1936. And it gives a nice set of operation called Markov moves on the set of all braids that give you all the class of all braids that have the same closure. So if two braids, alpha and beta, have the same closure, then they are related by conjugation. So let's see why. We have here alpha, and I conjugate by another braid, let's call it gamma, and here we have gamma minus 1. And now we can think of combing the braid and make gamma minus 1 slide along the trivial strands here and make it appear over here. And now gamma and gamma to the minus 1 just cancel out because they are one the inverse of the other. And so we obtain alpha here. And then the other operation is called stabilization, and this stabilization is just the inverse of this operation. And it's just consists of adding a strand to alpha and adding an extra crossing here at the end. And now if we close, we see that we obtain something that just has a trivial curl here that I can undo, as I was saying before. And then I obtain just the closure of alpha. Although the moves are quite easy and the statement is not that hard, the proof of this theorem is pretty hard. In fact, the first complete one is due to Biermann in 75, so more than 30 years later, so almost 40 years later. Okay, so this is a very nice theorem per se, but it has also a very nice consequence that is due to Jones in 84. And it's the Jones polynomial. It's an invariant of knots and links. So where does it come from? We have some representation of the braid group inside an algebra. That is something I wrote here, the formal definition, but we don't care about the formal definition right now. And here the formal writing of the representation, but I don't want to focus on that right now. We just need to know that the trace of this representation up to a rescaling is an invariant under Markov moves. And so Jones proved that this is an invariant of links that is called the Jones polynomial. And we define it with V of L. And it's a very important invariant. It opened a subfield of knot theory in itself. And we see here that it's not that difficult to compute, at least for knots with a low number of crossings. And we see here that the trivial knot is just 1 as Jones polynomial, while the trefoil knot has this Jones polynomial. And hence, this is a proof that these two knots are actually different. So we see an example of how to distinguish knots in this case. And to show that actually there is a lot of research to do about this invariant is that it's still an open question if there are any other knot with V equal to 1, or if it's just a trivial knot. We don't know this to this day. So let's go back to symmetries. what was the aim of my research is to put into connection Alexander Markov theorem with knots and links with symmetries, to see if there was an adaptation, a generalization of these theorems to the strongly invertible case. To see that, we have to introduce some type of braid, a braid with a particular type of symmetry, which is called the palindromic. So a braid is palindromic if I write alpha in the generators of the braid group I told you before, and then I read them from right to left, like in this case. And what I obtain is the same braid. Essentially, I mean, maybe this won't tell you anything, but essentially this means that if I flip alpha like this, rotating 180 degrees the braid, I obtain the same braid. So here, for example, I see an example. So if I rotate this one, I just obtain the same braid. And this is not an example. In fact, if I rotate, I obtain something that is not isotopic in any way. So when I have two palindromic braids, I can see that their closure is strongly invertible. In fact, if I put one here and one here, and then I close them in this very simple way, if I rotate 180 degrees, I obtain the same, like I can see that the knot is fixed, or the link is fixed setwise, and it reverses the orientation. So let's see here an example. Here I have a very simple, the one we saw before, braid, and here I have another one. And now if I rotate 180 degrees, I obtain the same knot, and this is strongly invertible. So what can we say then about Alexander theorem? We have a closure map. We want to ask if it's surjective, and what are the braids that have the same closure as a strongly invertible link. So what I obtain is that every strongly invertible link is actually the closure of two palindromic braids, and this is what I call the equivariant Alexander theorem, so an equivariant version of it. And then I obtain a version of Markov theorem. So if two pairs of palindromic braids have the same strongly invertible link as a closure, then they are related by a finite sequence of moves. These times, the moves, of course, have to take into account the symmetry as well. And these are three types of moves that I introduced now. These are the equivariant conjugations. So it's just the conjugation we have before, but we have to preserve the fact that alpha and beta are palindromic. So if I put gamma here, I have to put gamma bar here. Gamma bar here is just the reverse of gamma, the braid I obtained by flipping gamma of 180 degrees. And the same I have to do here with the gamma -1. Hence, these braids are still palindromic, and what I obtain is still a strongly invertible link, and is actually the same strongly invertible link. The second operation is called double stabilization and the inverse double destabilization, and it's just obtained by adding some curves, two curves like this, that have to be symmetric. So they have to be sent one to the other when I rotate 180 degrees. And the last final move is stabilization on a fixed point. So here, if in alpha, I see here a fixed point of tau, so a point that here is just on this axis, so it's not moved by the rotation, I can exchange it with a curl like this. And in this way, I obtain all the moves I need to say that the two closures are actually isotopic in an equivariant way. So this is the end of my talk. Thank you very much.
Thank you, Alice. Let me stop the recording.